Hello, everyone, and welcome to the first presentation of the second day of Big Mountain. Hope you enjoyed Catherine's talk earlier today. Right now, we will be talking about streaming data using Apache Pulsar and the
Hello, everyone, and welcome to the first presentation of the second day of Big.
I think there was some echo background. Have you heard that?
Yep, I think we're good to go now, Ricardo.
Okay, can you start?
Yep, already started.
All right, so thank you. So welcome everybody. I hope you're enjoying this presentation and this conference so far. It's been great for me personally. I'm learning a lot with the other speakers, so the content has been really, really great. So I'm going to talk about this concept of streaming data that has become quite popular these days. And for the implementation strategy, we're going to walk you through in how to do this using this technology called Apache Pulsar and the ElasticSearch, right? So what's going to be the role of each one of them? I'm going to actually explain this in a moment, right? So for those of you that don't know me, my name is Ricardo Ferreira, right? No matter to pronounce my last name. Ricardo is just fine if you want to follow up with me later. And I work as a developer advocate. So I like to explain that my job is basically connect content with people, right? Whether content is something that developers need to finish their implementation projects, right? I work for this company called Elastic, which might be well known for being the company behind ElasticSearch, which is composed by ElasticSearch, Logstash, Kibana, and Beats, right? Before Elastic, I used to work for Confluent. That's where basically all my background with streaming data came from. I was essentially working as a developer advocate as well there, talking a lot about Kafka and streaming data and things like that. And also I had some passages between Oracle and Red Hat. So if you want to follow up with me later, so those are basically the technologies and concepts that I like to shape my career. And basically those are the technologies that I like to speak about it. So streaming data, big data, NoSQL, cloud, those analytics, those are the things that I enjoy the most. And those are my contacts. If you want to send me some email, here's my email from Elastic. This is my email from my personal email if you want to reach out. And for those of you that use Twitter, follow me on Twitter. From time to time, I share some of my talks, presentations, and the content I produce regarding these subjects right here that I've just explained about. Right. So let's get to business. Before we start jumping straight to Pulsar and ElasticSearch, I think it's important for all of us to understand why streaming data, right? So there is this very interesting report from Forrester that is called Perishable Insights, right? And basically the outcome of this report is to analyze the perishability of the data, right? So what is perishability? Is the ratio about when some data becomes stale, right? So by the time the data happens, right, the data just happens, some application produces it or some downstream system produces some log, you name it, right? By the time the data happens, there is a small fraction of window that if you actually leverage that window to process that data and build some actionable insights on top of it, that's where you're going to be creating what we call a contextual driven analytics implementation, right? When you are actually going to leverage the power of data as they happen, right? And in order for you to do this, you have to leverage windows like real-time, seconds, minutes, likely some hours sometimes, but preferably you should be doing this in seconds or minutes later, right? What we call brick-and-mortar implementation for analytics, that's what we have been doing as an industry, as an IT industry for the last 30 years, which is we basically managed to acquire data and we're going to store it somehow. So we're going to process later, right? And that later might be something like hours, minutes, or even months later, right? Obviously, it works, right? Otherwise, we wouldn't be like doing what we have been doing for the last 30 years. But the point is, by the time you actually process a data that has been acquired and stored for months ago, right, you might be missing some very important element, which is the actual value of why that data happened, when the data happened, what was the circumstances that made that data to happen, right? So all of this is what we call, you miss the context if you don't process the data in a timely manner. When we're talking about streaming data, there are different use cases, as I like to call latencies, in which you are actually going to implement streaming data. So the first latency that we're going to talk about is going to be the microsecond latency, right? Millisecond latency. So usually when you're building microservices that has to share data between each other, it's like to use streaming data for this because it's going to be really, really fast to communicate all the changes and perhaps building architectures that are based on patterns such as event sources or CQRS or things like that. So that's one of the use cases that you can use streaming data, right? The other one is what we call log ingestion or change data capture, CDC, right? Usually that doesn't happen so fast in a scale of milliseconds, but it's still very fast because it happens in a matter of seconds. So if you have an inbound high stream of data coming in, you might be leveraging streaming data to actually observe, ingest, and store that data very, very, very fast, right? And also there is the use case that we call the streaming ETL. ETL, as you may know, stands for extract, transform, load. Usually what you're going to do this kind of streaming data implementation when you have a data lake or a data warehouse sitting somewhere that's going to be interested on the data sets that are coming from the data streams, and somehow you have to manage the volume and the frequency, right? Because the data lake or data warehouse were not built to accommodate that large amount of data, right? So you put a streaming data layer on front of your data lake or data warehouse that is going to actually shape that data in a timely manner, aggregate it. It's going to build a new data set that the downstream data warehouse architecture is going to leverage in a very user-friendly manner, right? And in a nutshell, the streaming data architectures are comprised by like these 5 layers commonly, right? Later on, we're going to talk about that one of those layers are not necessarily very, is a pre-requirement to build one, right? But in a nutshell, you have the persona of the source data, right? This is the data that actually is coming in a very continuous way, right? That this layer of the stream ingestion is going to, it knows how to read that source data somehow, right? It probably is on a programming language platform or framework that knows how to interpret that data. And what the stream ingestion layer does is essentially ingest that data into what we call the stream buffer, right? The name buffer is very intentionally here because it actually uses as a buffer, as a persistent buffer that where it can store your events and your data streams that can like survive for a very period long of time. You can actually reprocess them as many times as you want it, right? So those are some of the characteristics of a stream buffer, right? And optionally, you might have this layer of the stream processing, right? Which is going to be, as the name implies, is going to process all those streams before actually delivering the data to the analytics layer, where actually the fun happens, right? This is where the users are going to make their analogies. They're going to run scenarios. They're going to have some predicted analytics that are going to find out value across the data, right? So for this talk, we're going to be talking about how to implement this architecture that I've just explained it with Pulsar and Elastic, right? So the source data can be anything, right? That's one of the beauties of the streaming data architecture, especially if you are using in conjunction with a technology such as Pulsar that is what we call schemaless. It doesn't have any predefined format that you have to deal with in order to ingest the data. It can be anything like an array of bytes. And then for the ingestion layer, one of the good things about Pulsar is that it offers natively a huge variety of programming languages that are compatible with the Pulsar protocol and Java, C++, C#, Go, Node.js. And there's a technology from Elastic called Beats, where you can actually also use it for attach to your source systems and bring data into to the stream buffer, which happens to be Apache Pulsar, right? So Pulsar acts as the stream buffer architecture where it's highly scalable, it's highly horizontally scalable. We're going to talk about Pulsar in a moment, but basically the role of Pulsar is to buffer all the stream of events for either option A, you're going to later on process them using something called Pulsar functions, right? Or you can jump straight from Pulsar to Elasticsearch and Kibana for doing the analytics layer, right? So we're gonna discuss this notion of, all right, so why sometimes I have to use Pulsar functions or not. We're gonna discuss this in the end, right? In a best practices session, right? But for now on, just see this architecture as your reference implementation, if you will, right? Although you don't necessarily have to follow this architecture end to end, right? Okay, so let's talk about Pulsar. That's one of the coolest technologies that specifically I have been working for the last 8 months right now. Pulsar is, as the name implies, a project from Apache, right? So this is a brand new project. It is brand new for the sense of how long it's been GA at Apache, but it is a technology that has been used widely in other companies and for a while now. It has been originally created by Yahoo. So it's been used largely for process like trillions of messages per seconds or a day, right? And it's very scalable. And one of the key characteristics, I'm not going to deep digger into the key characteristics of Pulsar, but the only thing that I would like to highlight it here, the slides are going to be available later on so you can read as one. I'm going to only highlight what is actually I consider to be the key differences. Specifically, if you are coming from other technologies such as Kafka, right? So for example, one of the things that I like about Pulsar is that it offers you a unified model to handle both streaming scenarios and messaging scenarios, right? So as you may know, Kafka is very good for streaming, but not necessarily for messaging. So that's one of the things that you have to keep in mind. Just like any other technology is highly scalable, it offers some native computing power, which is pretty cool because you don't necessarily have to have another layer to actually implement your computing layer, the layer that's going to process those streams as they happen. And it's from scratch is being built for being multi-tenant, right? So what that means, which is one of the coolest things that I like about Pulsar, is that you don't necessarily have to have siloed deployments for Pulsar. For example, oh, you have a project A, and then we're going to have an infrastructure dedicated for project A, and you have a project B that has to have a new infrastructure just because I don't want to mix the workloads. So Pulsar has this concept of tenants and namespaces where you can leverage your deployments and still control them in an individual manner, which is pretty cool. It also has geo-replication natively. This is not like an enterprise feature that I have to pay for in order to get it. Like it's out of the box, straight from the Pulsar project, right? So the architecture of Pulsar is very interesting because this is one of the things that actually makes Pulsar what Pulsar does, which is offers high scalability and high throughput, right? One of the key things that you're going to notice on Apache Pulsar architecture is that you don't have, obviously you have the persona of brokers where conceptually is where your data from the producers and consumers is going to end up, right? But there's a layer called bookies or actually implemented using something called Bookkeeper, but we like to call this bookies, is where the data is actually stored in some sort of a journal fashion, right? So that introduces a lot of advantages for the architecture. One of them being it offers, Pulsar can actually address the problem of durability by don't necessarily have to do async writes on disk right after the producer sends the data, right? So all the data is actually stored in a sequence journaling style on the bookies, where the brokers are basically going to have cursor pointers or cursors, like they like to say, for those bookies where the data is stored. So this is one of the key advantages that offers high throughput during the ingestion part, right? But the other advantage, and personally is the advantage that I like the most, is that you can more cost effectively increase and like improve your persistent architecture without necessarily have to introduce more computing power. So for example, if we compare Pulsar with some other technologies such as Hadoop, for example. What is Hadoop? Hadoop is a bunch of compute nodes, we call data nodes, that basically runs on top of a machine that has both compute and storage, right? So in order for you to increase your storage cluster, you actually have to introduce more compute, although you don't necessarily have to are going to use that compute for absolutely nothing, right? And Pulsar, you can actually have just a few brokers, right? That's going to handle all the partitioning. All the partitions are going to be spread over the brokers, while the actual data is actually stored on the bookkeeper layer, right? And you can increase your storage capacity of your Pulsar architecture without necessarily adding compute power, which is, in an infrastructure perspective, is more costly, right? So you can, in other words, you can increase storage. We call this tiered storage, right? Without necessarily have to introduce more compute, which offers you a more viable and economically way to increase and scale out your architecture, your streaming data architecture, right? Another thing that I like the most about Pulsar, and one of the things that you have to consider when you are evaluating other streaming data technologies, is that schema register, it is a pattern that is very common on streaming data architectures, but in Pulsar it's kind of a native, right? Not kind of, it's actually native, right? It is part of the brokers, offers you a schema so you can actually store the metadata related to all the data model that you have for your topics, right? And this is not going to be necessarily either another layer that is going to be running in another infrastructure, which is, again, it all has to do about cost, right? It's going to be run on your brokers, again, in this layer over here of your brokers. And more importantly, this is not like an enterprise feature that you have to pay for it, right? It is native and straight out of the Apache front community, right? Which is pretty cool. So one of the things that this support for schema register offers for developers is, for the programming language perspective, you can actually leverage in a compile time, right, these constraints that you're going to have a more strongly typed programming model, right, where you can leverage those constraints. And behind the scenes, both for the producer perspective and the consumer perspective, all the schema evolution enforcements are going to be guaranteed by the broker, right? So just like a database, right? You have a data model, a schema, and that schema is enforced by the database. So you don't have the producers and the consumer don't actually have to worry about how that schema is going to be enforced and evaluated. This is on the broker side, which is offloads a little bit of the effort for the developer. So if you're considering streaming data architectures, this is one of the points you have to keep in mind, right? Another thing that I like about Pulsar, and if you're planning to implement any streaming data architectures in the future, is that it offers a very robust and hybrid messaging model. What that means is that, so you have the concept of subscription, right? So a consumer creates a subscription to actually read data from one or multiple topics. So this is what we call subscription, right? Within that subscription, you can have, obviously, you can have multiple consumers, right? So if you want to increase consumption throughput in your streaming data architectures, it's just a matter of putting more consumers to actually scale out your consumption throughput. But this is what happens out of the box if you are using something called a shared subscription, right? So all the consumers are going to actually load balance themselves to actually process as the data happens. So your goal here is throughput. But let's say that your goal here is not necessarily throughput, it's consistency, right? So you can actually change in a subscription layer, you can actually change from shared to failover, right? All these characteristics are kind of a knobs that you can set in your consumers, right? So it's all in the consumer side. And right off the box, you can have this concept of, all right, I'm going to try to deliver this message for one of the consumer only because idempotence and data duplication are important to my model. But if that consumption fails, the subscription automatically fail over for another available consumer, right? So the bottom line here is that only one consumer is going to have to receive a copy of the message because, again, consistency is what you are looking for. Or you can have what we call exclusive subscription model, where it's kind of like a queue, like a peer-to-peer programming, where only one of the consumers at a time are going to process the message. Maybe you are dealing with a use case where this makes sense, right? So having this hybrid messaging model, it's important. That's the bottom line that I'm trying to say over here, right? And this is going to be particularly important later on where we start talking about the integration between Pulsar and ElasticSearch, because exploring in a deeper details how each one of those subscription model works is going to help you to decide, all right, I'm going to choose using what Pulsar offers out of the box, or I'm going to do my custom implementation because my requirements require that, right? As I mentioned before, geo-replications out of the box is part of the Pulsar offers you, right? And you are probably going to implement this in scenarios where you have Pulsar cluster running in a region, right? For, let's say, West Coast of the United States, and you want to have a copy of your cluster in East Coast, right? Maybe in New York, that's being synchronized with the cluster in San Francisco, for example. So you can do this very easily with the out-of-the-box support for geo-replication, right? Maybe you're doing this for disaster and recovery reasons, or perhaps you're doing this because you want to improve the customer experience of your applications by maybe having the data that is produced in one region automatically replicated for another region. So whatever happens in the other regions can see the same data set that has been produced here on the other region. So this is what we call, if you're building a global strategy of your application where the data is global, this is going to come very, very handy. And obviously, the support offers you to handle both active passive scenarios as well as active scenarios, right? So it's pretty cool. Another thing that also is available out of the box in Pulsar is what we call Pulsar functions, right? So Pulsar functions in the bottom is essentially your processing layer, right? So a lot of technologies such as Kafka has this ingestion and storage layer and works pretty well, but you have to kind of rely on external technologies such as Apache Flink, KSQLDB, Kafka Streams to actually do the computing part, right? And Pulsar, this is actually part of the broker, right? You just actually separate you're going to nominate one of your brokers to be what we call a function worker that is going to basically handle functions, right? So you don't necessarily have to use another technology, right, in the mix just because you want to do the computation part as well as the storage part with your functions. And it's basically is a programming model that offers a function based, right? So if you ever wrote a Lambda function, this is exactly how a Pulsar function looks like, right? On top of the Pulsar functions architecture, there's another thing called Pulsar Io, right? Pulsar Io is basically the connector architecture. So if you want the Apache, if you want a Pulsar to communicate with external systems, either from the external system bring data to Pulsar, or maybe from the data that is in Pulsar you want to send to another external system, Pulsar Io is your guy, right? So this is the framework that's going to handle connectivity. And one of the coolest things about Pulsar Io and Pulsar as well is that there's a bunch of out-of-the-box connectors that are free and ready to use. I mean, you don't have to actually write, all right, I'm going to send the data that is on my Pulsar topic, I want to send to Redis or Elasticsearch. So I don't need to write code for it. It's just you grab the connector, deploy in one of the function workers in your architecture, and that's it. You're out of the box. You have data continuously being sent to your external system. So it is pretty cool. Now that I gave you this overview about Pulsar, let's discuss very briefly the ElasticStack. I'm not going to take too long over here because this is more for implementing the analytics layer, right? As I mentioned before in the diagram, ElasticStack is a technology, is a stack, as the name implies, right? That has been kind of created and evolved across the years by Elastic, right? So I like to explain the ElasticStack for the perspective of the user, right? So users or data scientists, they would like to play with the data. They would like to visualize their data sets. They would like to experiment with them. They would like to run scenarios to see if the data reveals something important that might be an opportunity or a threat to the business. So the layer that actually going to provide this is what we call Kibana, right? Kibana is a UI, the presentation layer of the stack, right? It's a very easy to use, written entirely in JavaScript, front-end layer for you to play with the data, right? It's very common for analytics user. But the data that is actually going to be worked out on Kibana needs to be stored somewhere. Kibana has to have a data layer to store all the data that's going to be worked out. And that layer is Elasticsearch, right? Elasticsearch, in a nutshell, is a very scalable, horizontally scalable, very easy to use, developer-friendly data store, right? You can be seeing Elasticsearch as a NoSQL database, if you will, but pragmatically speaking, Elasticsearch has been built to be what we call full text search database, right? So it is a type of database where whatever you store there is meant to be searchable, right? And it provides very advanced capabilities for searching, right? And data needs to end up in Elasticsearch somehow, right? So it's not going to automatically happen there to be stored there. So this is why we have log stacks and beats, right? In a typical streaming data architecture, that specifically the one that we're going to discuss here today, you probably not going to use beats and log stacks that much. You can, but you don't necessarily have to, because as I mentioned before, Pulsar on this ecosystem offers Pulsar Io natively. So this is probably what I recommend to use out of the box, right? As I mentioned before, Elasticsearch is the storage layer for Kibana, and that's why we call that Elasticsearch is the heart of the Elastic Stack. Without Elasticsearch, nothing would make any sense. And this is a very distributed, scalable data store that is highly available. It has a clustering model that is very robust, right? One of the things that I like the most about Elasticsearch, other than obviously being developer friendly and highly scalable, is that its architecture is composed by different, let's call, node types, right? So an Elasticsearch cluster, you can have different nodes. That's how you're going to address the scalability, right? Primarily, right? So all your nodes, you're gonna have a node type called what we call a data node, that is going to be the node that, as the name implies, is going to store the data. And those nodes can be spread over the cluster to form a universal global cluster where all the data will be spread over shards, right? If you're coming from the Pulsar background or Kafka, you can see shards as your partitions. It is fundamentally, from the distributed system perspective, it is the same thing, right? It's how you spread the data for address elasticity, right? But besides the data nodes, you also have what we call the master nodes, right? The master nodes are basically going to be used to form some sort of a consensus, right? Any distributed system has to have a consensus protocol implemented for handling scenarios such as, all right, one of the nodes fail, who is going to be the leader of that shard? So a consensus has to be taken, right? And there are dedicated nodes that you elect in Elasticsearch to be the master node. It can be 1, 2, or as many as you want it, right? Conceptually, you're going to have fewer master nodes and lots of data nodes. But also, every node in Elasticsearch is a coordinating node. Why? Because for the developer's perspective, they can connect with a single node in a cluster. And if that was not the node that's going to store the data being sent, it communicates with the actual node that hosts the shard. And then automatically, it moves the data sent by the producer to that node. So that we call coordination, right? And also, this is very important for the topic that we're discussing here. There is the ingest nodes, right? Ingest nodes are nodes that we can implement what we call transformations. And if for some reason the data that's being ingested into Elasticsearch is not complete or is not in the right format, you can run these transformations before the actual data is persisted to the shard, right? So that's why you have these ingest nodes. And optionally, you can have what we call the machine learning modes, where, as the name implies, you can run some machine learning algorithms that can analyze data and detect patterns, right? So now that we have actually discussed about Pulsar architecture very briefly, as well as the Elastic Stack and Elasticsearch, which is the data store of the Elastic Stack, let's discuss a little bit about the implementation best practice. In other words, how you are going to actually implement that end-to-end architecture that I've showed in the beginning. So the first thing I would like to point out here as a best practice is that Pulsar, actually this is one of the native features that I like the most as well from Pulsar. It offers you out of the box the concept of data duplication, right? Data duplications is, in a nutshell, a way for you to address the problem of, if something happens on the network layer, maybe one of the producers are going to try to retry to write the data that has been ingested. And because of that, you might end up with duplicated data on your Pulsar topic, right? In order to avoid the situations, you can enable the duplication on Pulsar, right? This is something that has to be configured both in the broker level. So there's a knob that you have to go there and Pulsar explicitly and turn it on, as well as in your producer code, you have to set some information such as the transaction ID and things like that in order for this to actually work. It works beautifully, right? But the point here is that you have to explicitly turn it on because by default it's off, okay? In order for Pulsar to actually send data to Elasticsearch, right? Remember, the analytics layer is going to be based on Kibana, right? That in turn needs data that is stored on Elasticsearch, right? So for the architecture perspective, it is your job as architect and the developer of this type of architecture to have a layer that is going to be responsible for whatever data has been stored on Pulsar needs to be sent to Elasticsearch. In my personal experience, I have found that implement this using what is native from Pulsar is the best practice, right? And what is native from Pulsar, that we have discussed before that allows this to happen? The Pulsar Io Framework, right? The Pulsar Io Framework works very, very interestingly because you can have in a Pulsar cluster, you can have a bunch of nodes that are going to act as brokers, right? Such as what we are seeing here. But you can have the same broker. It is the same software. It is the same bits that you are going to spin up in a container, virtual machine, or host node, right? But you can change a flag in the configuration of that machine, of that broker, that from that point on, that broker is going to act as a function worker, right? In other words, it's good, just like the architecture of Elasticsearch. Remember data nodes, and then you have the ingested nodes. Here's the same thing. You have the persona of the broker responsible for data storage and ingesting, buffering, as well as brokers and nodes that are going to be responsible for basically computing, right? So the Pulsar IO preferably has to run in a dedicated set of nodes exclusively for the sake of sending data out to Elasticsearch. That ensures high availability. Obviously, you have to have at least more than one node, and also address the problem of not overloading your broker nodes that are responsible for storage with tasks that are dedicated for sending data out, right? So this is the first best practice. One of the things that the connector specifically that comes with the Pulsar does is it automatically creates the index for you on the Elasticsearch side. So you don't have to have this administrative task explicitly, right? One of the things that I would like to point out, the data that is stored on your Pulsar topic has to be JSON already. So that is a responsibility, architectural responsibility for your producer, or maybe some other layer that's going to transform the data before writing to the stream buffer, right? And the connector kind of controls acknowledgement per message, right? So if you send 10 messages, you might have 7 of them that will successfully write on Elasticsearch and 3 of them that might fail. If they fail, the cursor of them on a Pulsar side would not be committed, and therefore there will be retries, right? Which is good for handling failover scenarios, but sometimes might be bad, specifically for the point here on the bottom, because keys are not converted to IDs and the documents that are written into Elasticsearch. So messages in Pulsar have keys, right, which are identifiers, and documents in Elasticsearch has IDs, right? So like ideally, the key from Pulsar has to be transformed in a document ID from Elasticsearch. So this doesn't happen automatically. So for those of you that know Elasticsearch, you know that if you don't specify an ID on Elasticsearch document, one will be automatically created for you. So what's going to happen is that in the scenario that I was explaining before, the 3 documents that fail to be written in Elasticsearch, they will be actually reading like twice or 3 times, right? But for the Elasticsearch side, there will be like different copies and that have unique IDs of the same message on the Elasticsearch side. So if you're too much concerned about consistency, you have to pay attention on this, right? And somehow put the key on the message that will be sent to Elasticsearch. And one of the cool things that the connector does, it supports like Elasticsearch before the version 6.2. Why this is important? Because before that version 6.2, Elasticsearch has this concept of indexes that would be databases, and a database that would be broken down into types, right? Now, this concept doesn't apply. The current version of Elasticsearch is 7.9.1, and now you don't have more types. Everything is a type out of the box. So every entity of your domain model will be an index. So this is how we differentiate. But the point is, the connector from Pulsar knows how to handle this between versions, right? Let's go back to that discussion that I've mentioned before about, right, do I actually need Pulsar functions in my end-to-end architecture? So just to recap, I have my source data that's coming from somewhere that I'm going to use some of this stream ingestion techniques, programming languages, frameworks, or maybe tools like beats that could be used to read the data from the source and then ingest into Pulsar, right? So the point is, do I actually have to have Pulsar all the time to send data from Pulsar to Elasticsearch? And the answer is, it depends, right? Like everything else in IT and architecture, right? So I think that I put here some very challenging and provocative questions that you should ask yourself before having this decision very clear. So the first one is, you have to know where your data lives. So for those of you that come from the mainframe world, you might remember the concept of system of record, like which system acts as your system of record? Where is your gravity about where the data, what is the source of truth of your data, right? If you're using Pulsar to be your source of truth, then you might need to use Pulsar functions to maybe transform the data that is on Pulsar before sending to Elasticsearch. But what if you want to use Elasticsearch as your system of record, right? So in this case, you can actually pass through the data as is from Pulsar to Elasticsearch and bypass completely the Pulsar functions layer. So you don't need to transform anything because the transformation layer, the Elasticsearch technology offers you a very robust set of transformation technologies, aggregations, filtering, search, that you can do pretty much everything that you would do on Pulsar functions, you can do on Elasticsearch. So it's more like, okay, the first question, where my data will be the system of records, Elasticsearch or Pulsar? That's the first question, right? Also, which type of transformations are you going to use, right? Depending on the transformations, the Pulsar functions might be a little limited for what you are trying to implement, right? Because Pulsar functions are supposed to be meant to be more stateless as possible, right? But if somehow you have to do some computation that needs to kind of bufferize a sequence of records, perform some logic computation, it might be more interesting to bring this kind of a computation to the Elasticsearch side because it offers this out of the box, right? Same goes for aggregations, right? Depending on the type of aggregation that you are trying to do, it might be interesting to leave this through Elasticsearch instead of doing this on Pulsar functions. And I'm not saying this because it's not possible to do this on Pulsar functions, right? It's more for the sake of how much effort are you going to have, do you want to have in your implementation project, right? So in my opinion, and I have done this explicitly, both in Pulsar functions and Elasticsearch, it works in both of them, right? Very few scenarios are not supported in Pulsar functions that you need an Elasticsearch. But the bottom line is that everything you can do. But Pulsar functions is a programming model, right? You have to literally pick up a programming language, write code, compile, deploy. Maybe you have to kind of turn one of the nodes down, the cluster down in order for all the deployment. I don't know what your deployment strategy is. The point is, maybe if you don't want to handle downtime scenarios, do this on Elasticsearch because there's no downtime there, right? For transformations and aggregations. And also, I think one of the things that you have to take in consideration is, what is your technical expertise of your team? Maybe you have a bunch of data engineers that are very knowledgeable and skilled, but they're not Java developers, right? Or they're not Go developers, or they're not Python developers. So why actually have to teach them and train them into a programming language just because you have to use Pulsar functions, you know? So that's the architectural discussion that I would encourage you as a best practice to have with yourself and your team before I actually start implementation. Because sometimes what I have seen in the industry is that we developers, and I include myself on this, we have this tendency of, all right, what is the kind of a blueprint that I have to follow in order to ensure the success of this project, right? So, oh yeah, I've seen in a presentation on the Big Mountain and Dev Data conference that there's a speaker that said that you have to have Pulsar functions in order to have a streaming data architecture. No, this is not true. This is why I am emphasizing this, right? You have to use your best judgment for it, right? And also, another point that I like to emphasize for this decision is that what is your infrastructure gravity? This sounds silly, but it's very important, right? Because the infrastructure gravity has to do with most of the times there are layers in software architectures where we have full control of it, we have full autonomy of changing, right? And perhaps might be your Pulsar cluster, right? You have full control about what to do on your Pulsar cluster, right? For example, yeah, I have the ability to change if a node is going to be a data node or a function worker, right? Or maybe you have more this autonomy on the Elasticsearch side where you can actually pick and change a lot of things and do the change without necessarily having to have approval of your boss, of your team leaders, or something that involve it with your project, right? So you have to figure out what's your infrastructure gravity, right? Where you have more autonomy. If it's on Elasticsearch, right, it might offer more peace of mind for you to actually live this this part of the computation on the Elasticsearch side, because you have more autonomy to take decisions such as, all right, I'm going to scale out the cluster, I'm going to put more nodes, and those nodes are going to be ingest nodes just for handling transformation and aggregations. And I don't necessarily have to kind of pass through a bunch of very difficult argumentations with my team or my company. So know your infrastructure gravity, right? That's it that I would like to share for now. So from this point on, I would like to open for Q&A. So if you have any questions that are specific to how to implement streaming data architectures, both in general, as well as with using Pulsar and Elasticsearch, I'll be more than happy to address them.
Thank you, Ricardo. Anybody who has any questions, please either use the Slack room for BMDD_room 3, or on the right side of your screen, you can type in a question.